The title intends to be a little bit short, but you will see if I'm able to move on to the following slide. And I thank my colleagues from Belgrade, from Board, for this, because I simply use their template for the second slide and put all the lettering that you can see in there. I will give a kind of personal, but also related to lots of literature view on what is the meaning of artificial intelligence in mining and in raw material field in general, how Industry 4.0 has been implemented, and other concepts that you can read through. Some of them I've been acquainted with, as I mentioned. Some of them I haven't. I haven't yet flown a satellite, for instance. But you will see that there is a link permeating the whole stuff that I'll be talking about, which is the ubiquitous presence of computers everywhere. With them, we have to do plenty of the work in analyzing and providing data, which is one of the more important words that we have around in these days. So with this, I will just throw on some concepts. And what would you think if I told you that the next couple of slides were written using the ChatGPT? Maybe you will laugh about that. But I thought that it would be interesting to try to see what happens in what I wanted to express and how the machine will try to express this and give it back to me. Of course, I had to do some polishing because it seems that this tool tends to repeat itself a lot. And when you ask something, it simply repeats what you said. And at the end of the paragraph that it writes, it does it in some other wording again. But somehow, this is what we will find sooner than later. We will have to deal with tools that will gather all the information they have around and learn by themselves. And this is the subject-subjacent idea below all artificial intelligence. If it is to be called intelligence, it's supposed to pass the Turing test. So it should be indistinguishable from a human at the moment. In my attempts with this tool, ChatGPT, I think everybody could distinguish that. But if you go to some fields that are closer to real computing stuff, so for instance, try to solve this problem for me, writing a program in Python. You will see that in time, with a few interactions with the machine, it learns somehow from what it has somewhere in its data servers, and it will give you more or less a correct answer that later, if you're an expert, of course, will help you in your process. Now, this is not intended to be something that the students in the first year undergraduate should use, because they will easily get caught, I think. But what I'm trying to say is that we, professors, need also some education on this as well, because reporting and sending something in a PDF will be under suspicion from now on and probably forever. Okay, about those concepts I was mentioning. The first one is on exploration. Exploration is always at the beginning of a new mining project, for instance. What can artificial intelligence do for us? Well, of course, what will we do? Improve all that is better and try to earn more money and faster. So a good example would be that machine learning algorithms can be trained and taking some geophysical data that can be drawn on the field, or maybe taken from Copernicus, as we will see later, from our raw material information system, or from some data from some colleagues, or from the literature, we can more easily identify areas in which we may find out where is the material of choice. Let's see, for instance, we're trying to find the so important rare earths, and as you already know, in this mine in North Sweden, they have found close to the iron ore, they have found some interesting deposit, probably of rare earths, and this has been done using exploration tools linked to machine learning algorithms. In the operation itself, it can improve safety, but you can see again the wear efficiency. This is, as I said, the first sentence is taken from ChatGPT directly. Okay, you can see how repeats a lot, mining and repeats operation again, etc. So where would this go? Okay, there are ongoing efforts on having more and more autonomous mining equipment, and not only the equipment, but also the operational way on which these types of enterprises and endeavors are tackled. And the idea is always to reduce the risk of incidents, but at the same time, mine faster. So we can optimize, for instance, processes as the blasting of rocks or the drilling. I think on the other, you have some of this during these webinar sessions as well, and also predict when the equipment is going to fail. And for that, you will need a lot of sensors. And sensors basically take data, and this data are ever coming in more and more and increasing amounts, and they are difficult to handle by typical human operators or typical programming. So tools linked to artificial intelligence help a lot in this regard. For predictive maintenance, to increase the duration of our equipment, this will of course save a lot of money, or for processing itself to try to reduce the waste that is produced, or again, you can see the wear efficiency, recover materials, and try to leave in the scrap or later on in the tailings the least amount that can be possible. No? This kind of data processing linked to blockchain techniques and the Internet of Things or so on is not exclusive of mining, but it permeates all the industry 4.0 and also 5.0 initiatives in many other fields. Okay, we can improve the handling of waste to draw out some secondary raw materials. There are ongoing initiatives at the European, well, and worldwide levels to try to reduce our wastes. This has been going on for a while, and if we can benefit from what we have left behind and convert this residue into an active, the people leading circular economy initiatives would be extremely happy. Modeling, I mean, this is the field in which I can consider myself a little bit more expert. So in this case, we can model, we can simulate what is the operational field. And there are lots of experts going on. We can try to minimize the usage of some kind of valuable and critical raw material to build up our mining equipment, drilling machinery, cutting machinery, for instance. In this, I have some experience. But we can also use that to increase the recovery rates in connection with all the fields that we have presented before, to help deal with better usage of the machinery that we've got at hand, to minimize the downtimes. So modeling is there to save money because it only uses computing, sometimes high performance computing, but which is always less costly than the rest of the processes that use many times a trial and error procedure. About safety monitoring, of course, we can have cameras, we can have all kinds of sensoring equipment to check out what happens. I mean, my grandfather used to be a coal miner here in Asturias, and in his times they used even birds to get into the mine. This is not happening anymore, so we can have lots of monitoring equipment that we can check out in real time to improve safety. And then there is the what I would say the meta mining field. Data mining is trying not to reinvent the wheel, to analyze all the heavy, ever-growing amount of data that we obtain, and we have lying and hiding down under piles and piles and piles of archives and directories and so on, and try with that to identify patterns that will help us to go directly to the solution that we want. And if this has been done previously, this can help to save a lot of time when we design new projects. So there are new techniques that create Dockers or information containers in which you can store and you can share information. And with this, there is something that is also very important, that is the ontology field. Ontology basically is the, well, quite simplified, the nomenclature, something that the other machines that are querying, that are questioning our database can access and can extract information from independently of how this information has been generated. So this is kind of some computational operation that helps you to refine, funnel what you need to obtain, and then get on your side just information you need from a billion, sometimes large entry database. Okay, so as a summary, artificial intelligence increases safety, increases efficiency, of course, increases sustainability by helping to recover materials that may be valuable, helps productivity, so more money for the time that you're devoting to the whole process, and of course helps to increase the accuracy of our procedures and, if possible, the speed, not only in the industrial process, but also helping to make better decisions and faster. Okay, I cannot see if there are questions or anything. If you allow me, I can also switch on another computer that has on idle. Sorry for that. And I have this open as well there, and maybe with that I can have some input. So what do we want? We want to improve. The office telephone. Sorry for that. So we want to ensure, if possible, that we have enough supply of valuable raw materials to drive our industrial revolution. So to go green, to minimize our waste, to try to bend down the global warming, all these kind of things, to be more responsible, to help others. This is, in fact, what is behind all our technological and scientific initiatives. No, this is the best field to work in because you're trying to help people, not only help yourself to get a brilliant career and so on. So with this, what is important is to try to find a good solution that can be tackling some kind of application that we want to improve. And in this table that is taken from the paper that you can see below, I hope, there is an application area, there is a kind of solution, and we discuss the advantages and disadvantages. So for instance, if we want an autonomous machine, we want an unmanned machine that can be helpful and can be helping us. This would be helpful not only in mining, but also in protecting the roof of our operational ground, to help also in drilling and blasting, crushing of rocks, to help with transportation. This is already done. There are big trucks that are taking the products outside of the mine, etc. And there will be plenty of advantages. And if you take a look at there are also some disadvantages. And if you take a look at the column at the right, okay, I think I can change this to some kind of laser pointer, but it's not really relevant. You will see high implementation cost, high maintenance cost, high implementation cost. So takes money. At the moment, lots of these technologies are already available. The problem is that they are costly. And as probably everyone around knows, from starting the exploration and having a project that is ongoing, there are a few years, and there should be some kind of sustaining budget that is able to cope with this. Of course, we also need, as you can see there, because I'm focusing on disadvantages while you read all the rest, because you could see that we have also a need for specialized stuff. So this kind of webinars, in my case, it only gives a glimpse of what is the field, but what is important is that everybody's trained to use these new technologies if they are implemented in their field. No? Not everybody will be sitting behind a computer as I'm sitting now. There will be people on field, but probably in the future, apart from some robots, etc., the persons that are working on field, they will have lots of machinery that is connected to the web, and they already have, and will give them information in real time on what is happening in the place of work, in their workplace. So we need lots of people that are expert in the handling of IT technologies in general, but nobody can know everything. So there will be probably an increasing grade of specialization, if you want to my opinion. Now, there are things that are funny. I mean, you may take a look, like these chips that are identifying employees. So they are good to know if somebody, I don't know, has fallen and maybe has passed out, and we need to find him. And the problem is that employees would see this as some kind of surveillance, and that they are not relied on, so nobody trusts them. And this is kind of linked to other webinars that we have had in this series that need to, talk about how it will be possible for people to accept the changes. No, there is a lot of education going on. There is a lot of divulgation. There are lots of things that have to be done before this is widely accepted. Not only mining, not only in the raw materials field, not only materials, but in every other industrial initiative. There are other things. You can still see here that we need qualified staff. You can still see these high equipment costs. You can still see that there is a maintenance cost. There are things that are special, which, for instance, if we are all going digital and we have lots of data, what do we do with that? Okay, we have to protect that, because there will be threats. There could be hackers around, there could be viruses, there could be ransomware attacks. There could be lots of things that will not be nice. So we have this sometimes lovely world of internet connecting everyone in every part of the world. Probably you're watching me or listening to me from many places all around Europe, at least. Maybe this is looks to some as kind of science fiction, but it's not. It's something that is already happening, and we need to be warned and to try to minimize the problems that we can encounter later on. So, of course, the advantages are always efficiency, safety, earning money, minimizing the errors, etc., etc. So, but the problem are the disadvantages in my case, in my opinion. So we need to convey to the end users, in this case, that are not only the CEOs and the CTOs of the companies, but the workers there, because as you know, some of the companies are really huge in number of employees, that this is a need, and this is something that has to be impregnating our work culture. This is here to stay. So it's not something that is going away, even if it has some risks, and we've experienced this always at times. There are downtimes, there are blockouts, there are things that may happen. The curve is ever increasing steadily upwards in the usage of computing technologies in general. Okay, So here is a flow chart that is showing the core of the industry 4.0. Let's say this box is a flow chart, so the segments of the industry in mining. I mean, as a whole, we need to increase to model our manufacturing processes. So we have this exploration. Well, coal mining is because of the example taken by these people. Probably this is because it is very well known. So we need if you can apply this to any field, no? And you can see in red there is some transverse communication that uses IoT. IoT is the acronym for Internet of Things, and also some automation and robotics. And the idea there is that everything that is leading to a better processing and a better working in a given project will have to handle these kind of concepts as efficiently and as productively as possible. And this has already been implemented in the mining 4.0. Yeah, now you may wonder what is mining 1.0. Mining 1.0 is the one that was led probably by the Industrial Revolution from, I don't know, the beginning of the 20th century. And then when we had electricity around, there came Industry 0.0. This was a major upgrade. So we had internal electricity, we had combustion engines working around, we had trains, we had then later on trucks, things like that. This was the 20th century mining. No? Nowadays we have, let's say, mining 3.0, in which we have higher power densities, of course not always from fuel combustion means. We have global GIS equipment around, so telemetries and sensors, etc. We have some kind of unmanned equipment. We have computers. We can store this. We can really handle things later on and see what has happened. But nowadays in mining 4.0, everything has to be done as much as possible in a hybrid manner and on the fly. So there should be ways of steering how something is going south, is going wrong, and from there on try to modify this as fast as possible and in real time. And this is what has led to a new paradigm, sorry for that, paradigm, which is mining 4.0. Now, you can see there several stuff that has been entering the field, no?
Sorry, Professor Roberto, I have
Yes.
There is a question. Ramona is asking.
Yeah, I cannot see that. Is it the problem is, yeah, I'm sorry for that. If you can, yeah, tell me.
Yeah, it says that, Ramona, you can ask by yourself or you want me to? Okay.
I thought I could see that, but.
Okay, it says that, what is your opinion about digital twin? And is there meaning to apply this technology for an already operating plan?
Okay, I'm talking about this a little bit on later. This is kind of, I mean, for me, my opinion, personal opinion, digital twin is a nice word for a simulation. So what you're trying to sell there is that you are able to replicate what happens in the real field. And for the moment, I think this is quite immature, in my opinion, because there are lots of complex things going at play. Okay, so as a physicist, what we tend to do is to simplify the model. And if you could say, okay, I'm doing a digital twin of a given process and focus on that. This has been done, but the problem is the interconnection between all of them to develop something that is widely and wholesome for the whole project, for the full project. And this is, I think, work in progress in that regard. but not also here in mining, also in my field. When we discuss multi-scale modeling of materials at different times and length scales, what we have is that the problem is linking all these several processes that take place at different scales, different times, different time scales, different length scales, and taken by different machines or different people and integrate that. But field is moving fast, and I would say that maybe at the end of this decade we have something going on. Now I can read your questions. So I was able, if just in case, okay, Lina, I can read the questions. If they are written, I can read them. What I cannot do is to open another window in Teams, because then I have this kind of return that is not good for anyone, I guess.
Okay, no worries, and I will be here listening, so it's okay.
Okay, Ramon, I don't know if I answer your question, but
yes, thank you.
Okay, in an already operating plant, I don't see it. I don't see that anybody is going to make the expense at the moment. But in new projects, maybe in time we will be probably obliged to do that.
Okay, so you believe that it's quite immature at the moment. So, yes. And because of the integration of many things, in order to this be efficient to install. Okay, yeah, I see that. Thank you.
It would take money again. Thank you.
Yes, but you can eventually you can not lose so much money. I mean, you can prevent many things.
Okay, of course. You need to have some projection. I mean, you need to know that your project is so good that you can make these upgrades. And some of them can be done while still working the other way. This is the idea, but not at the moment as a whole. So
from my understanding, you need many input data that maybe you don't have.
Yeah, of course. First thing would be to be able to monitorize what is happening already. So you need some increase in your sensoring, in your data. And this only happens with new projects. The old ones, what you have is archives. You know what I'm saying? When I talk about data mining may be going to a library or going and talk to someone who is 70 and is about to retire and knows how things have been done, and they have their tricks. And the problem here, this could take ages to discuss, but I think it's a very nice thing. How do you get the expertise from someone? Not from somewhere, from someone that knows how to do it. How do you convince someone to explain, who's been an operator in a given field for 40 years, and to take notes and get this information out of him? You know, it's like researching on the field. You go to a village and you ask the people there about folklore, songs, old songs and things like that. So we did this. And how do you know this? Oh, my grandfather told me this. And
or intuitively at this case.
Yes. It's this know-how, which is human, is the most difficult to obtain, in my opinion.
Yeah, right.
But I think this would be a good idea, a nice idea for a project which is interdisciplinary, you know, with the people that know about social stuff. So, I mean, before, some people that have been worked for a while in this, let's say, more conventional mining 0.0 projects retire, and we don't know how they did these things. It would be good to gather all this information somehow and to listen to the older, which is always good, in my opinion. But I don't know how to do that. I mean, everybody could go from one place to another and ask questions and note this down. And then this should be available for everyone. And this is where data mining takes a role. But before that, you have it only in the brains of someone. This is not easy to obtain.
Like actually, it sounds like a good future proposal.
Yes, 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 I give it for free. We can work.
Let's do it together. Anyhow, you can continue. Thank you.
I think it is the human factor. I mean, we are doing this because we are humans and we want to have better lives for everyone, for our children, no? I mean, this is the idea, yeah. But we have to worry also about what happened in the past. We cannot forget this. Everything goes that fast that we tend to forget the humans. And we should worry a lot about humans because this is what matters in the end.
Yeah, you're right.
Okay, so continue. Okay, you don't mind. Okay, I have to click on again. Okay, so what are the impacts of digital implementation? No, you have impacts. I mean, this we have also already discussed, but this is in lines. You can see it's in the exploration field, in planning the project, and then later on developing it. It's important when doing the actual construction on site, and then it's important when trying to extract what we need from there to operate, to improve the distribution, for instance, the transportation, the motion around the site, all these kind of things. And also it's relevant in marketing, in sales, in advertising, in everything like that. But there are things here that are really very exploration, for instance, is very important for mining and it's kind of a highlight. But sales and marketing is important for everything, for any company. So we can, and it's already being done, learn from other places and other companies that have already been doing this. In my opinion, what is important is that we have somebody around that learns where to look. And as I said before, and I tend to say this a lot, not to reinvent the wheel. So if there is another field, industrial field in which something has been already applied, should be able to say, okay, this works here. Why don't we use it here as well? Okay. And nowadays, people that work in the raw materials field tend to be very innovative and tend to try to bring new applications of whatever they can as far as possible to their projects. And this is kind of a change in the mentality that has been going on for a few years, maybe a couple of decades already. Okay, so as you can see, I have some supporting stuff, but I tend to talk on that. You can read whatever you have there, and maybe what matters is what I'm saying behind that. No, okay. There you have something which is a knowledge graph. This is something that is also very from the informatics, no, from computing engineers and telecommunication engineers and this kind of people. You can see that, for instance, this is an example of equipment maintenance, no, for a coal mine, to keep it simple. And this is also because I found this paper that you can see below, which is in a journal that probably nobody would access, Mathematical Problems in Engineering, which was pointed to me not by ChatGPT, but from our applied mathematics department that works in fields like this. No? So I tried to say, oh, where can I look something that has to do not especially with mining, but with industrial processes in general? Oh, this journal is not bad. Okay, so you can see lots of things there that bring about what is normally called an architecture, which is kind of a modeling on how to approach the process. And the idea here is that there are words that maybe you can skip that are important for people that work in maintaining the equipment. Semantic. Semantic comes from language. So this is, again, how do we interpret words? And this has to be done by a machine. So the vocabulary. We need some kind of programming that allows the software that we're using to learn and to interpret the words. And in some places, they call some mineral in some way, and in some other places, in some other. Or some fragment of a rock has a name, and some has some other. Mining has been very local through ages. And this is not only about the language itself, I mean, English, Spanish, Serbian, Greek, whatever. No, I'm not talking about this. I'm talking about the ways to express things. So we need also some kind of things that go visual. So we need to be able to interpret pictures, to interpret videos, these kind of things. So this is not really easy sometimes. And for that, we need some pattern recognition. Of course, in other fields, it has been already done, even with human gesture, human faces, human eyes, etc. We can try to apply this also. And this is done kind of routinely with drone imaginary, for instance. We need also to find out relationships, to find out ways of doing our pre-processing, the process itself, and post-processing. We need places in which to store our data and to be able to query, to interrogate our databases, to find out what is the best programming language that can access this. For instance, in Argonne, they have some kind of software, I don't remember exactly the name at the moment, that is devoted to mining processing. I can check this out later if needed. Or in Boulder, in Colorado, in the School of Mines, they have also some interpreters of metallurgical information and mineralogical information, these kind of things. And in the end, I have here this kind of ontology. No, so we have to be able to analyze as fast as possible what is happening in our field with a common language and their common approaches, to be able to have a common architecture. And when I say architecture here, I'm meaning not physical equipment, but a logical equipment. So you can say this is software and not hardware, to be able to access all the documentation and to provide new, and to be able to upload it and to be able to interpret it, not only in our physical place, but elsewhere and in similar projects that our company and maybe others, ideally, we should be able to share this kind of information. I know that everybody is there for earning money, and there will be patents and things like this. But in materials modeling, for instance, there have been ongoing efforts for having a common ontology for, I think, about maybe 10 years. And nowadays, all the really big also databases that we have around in Europe, the US, China, etc., they have found a common ground. And they are signing agreements on that. This is very nice because, as you know, from Europe, we can have to be as open as possible and to share the knowledge, be open source, maintain Creative Commons licenses, things like this. And this is difficult to reconcile with earning money from a company. And I think finding common grounds and finding words that, in the general sense of a word, that our engineers, our operators, our CEOs, our legal departments, etc., are able to handle kind of smoothly. This is something that should be at least attempted, no? If you want to go on with projects on that. Okay. Well, this is more on the same. This is kind of a vertical flow chart, kind of a decision tree. Well, the symbols really are not that much important at the moment. The idea is that we should be able to go from the physical process down here to the it's like a building, no? To the higher ground in which the decisions are taken. So for that, what is really important is that we fill up our site from sensors, actuators, analyzers, kinds of experiments that deal with data acquisition. We have some computing that is able to control that. Then we flow this into our mining software, so to say, and then we are able to integrate this in some kind of portal, if possible, in which everybody can access and easily interact and search and whatnot, and so on and so forth. And this is not really simple because of the extreme amount of data that we're probably handling, but this is the way to go. This should be how it should be done in all the subsequent attempts to implement Industry 4.0 technologies, and not only, also 5.0 and so on. No, imagine that you want to do, this is now sometimes in the news, a mine in the moon or in Mars sometime. I mean, everything has to be done remotely. Because it's a very harsh, extreme environment. So you need to have lots of things that are ready for that. I mean, for me, this is kind of still a crazy idea, but crazy ideas have been driving our progress for a while, you know, as everybody knows. Everybody thought that it was impossible to launch rockets or satellites, and we have them around all the time. Okay, now, about the processing. We can also say that this is a, let's say, well, I don't know if this is the correct expression, high-level architecture of the implementation of Internet of Things, blockchain modulus for inspecting a mine. And you can see that somewhere over here there is a cloud, and there is some, I mean, this is normally the symbol, the icon that informatics people tend to use to describe databases. No? So this is a place in which you store some information, and there will be people remotely working on their computer to interpret data. There will be people also doing reporting and telling off that somebody has done things wrong. And on site, you will have people with some kind of mobile apparatus or some kind of mobile sensor or some kind of digital equipment that takes all this data, even with them knowing probably, but with them having to intervene, to participate. And with that, we can maybe check out if the pressure on the wheels of our truck are correct or not, and if they are not, take some decision and stop it and try to bring some equipment that can solve that problem, or conversely, try to bring it to a place in which we can repair that. Everything. Look, what I'm trying to say is that this is I think the word is multi-tier system. So there are several levels. The architecture should fit with a real mining scenario in which we can be able to obtain data. You could say they are experimental data, they are field data, and try to model what a remote inspection could look like. Of course, having a nice internet access is extremely important, and this is not always possible. I mean, this is in a hyper-connected world in which we can have satellite communications, if not some other kind, at hand all the time, continuously, and have all the everything monitored. And this is not always the case. Depending on the processing, depending on the conditions, depending on the remote site that we are dealing with, even can depend on the country. It's really a challenge at the moment. But really, I was going to say slowly, but not really that slowly. Everything is going in the direction of having this sooner than later. Okay, this is a more concrete application. I mean, here before, sorry for that, we could see something that is more generic. Now we could move on to some kind of artificial intelligence as the computational scientists interpret this. And this is a neural network. And neural networks are really designed as something that represents what happens in the human brain or any other complex animal brain could be said, in which we have several layers. We have an input, and we need to find some output. And internally, there are connections between all the inputs via some, in this case, they are called neurons, but it's a layer that is hidden because it is programmed into our computer, in which there are checks of all the possible interconnections that we could have between the input and the output that we want to produce. Now, neural networks as machine learning techniques, what they are very good is as I am in interpreting the weather that we had yesterday. So they are very good with interpolating, but sometimes not that good with extrapolating. Extrapolating is where the real problem lies. Extrapolating is where we can may find some new concepts and new applications and new realms of opportunity. Okay, so this example that is taken from a journal from DPI mining, we're trying to build up a neural network for rock blasting. What would you need for that? We will need to take all the data that we can have and we can implement in our machines and try with that to find out where the rock would fly out and increase our safety measures in that regard and know where to find them. So this is a kind of back and forth, or English say back and forth. I would like to say forth and back. No, first you go from left to right, and then you go from right to left. What you need is to have some good data to train your model. When you have trained your model, you can leave some of the data outside and use them for testing. So this will be the testing data. And when you have this at hand, you go to the field and you check this out. If you check this out and it is correct, perfect. But if you want it to be as transferable as possible, so you want it to be extended to as wide as possible output, to be able to extrapolate what is happening with iron mine to another place in which has some different kind of mineral, to an aluminum mine. You want to work with bauxite or whatever. So you need to train again probably your model to improve that, and it's an iterative process. Iteration or iterative is something that computer scientists discuss a lot, no? And this is the equivalent to the older trial and error process. The problem is, the good thing about this is that this normally done in a computer and saves, in the end, time and money. Now, ideally, we should try to avoid the Edisonian approximation of having something checked out and then commit errors and then go back to that, etc. With the computer, you also do this. But you're not going into the field and maybe killing someone that is around because your rocket that is flying moves instead of 10 meters, goes away 25 and destroys some important equipment. No, I don't want to be that dramatic. The idea is that this is done with the highest automation as possible. Now, what is the criticism to this kind of models? The criticism is that the hidden layer is a black box, and there is, in my field, there is few physics involved sometimes, and there's few engineering involved as well, and there are lots of statistical and mathematical stuff going around that is not always easy to understand. Okay, don't worry. There will be people that are specialized in this field that will care about that, I guess. What I'm trying to say is that there is a big opening to people that know how to do this, that are not trained in conventional mining schools or material science schools, and that are able to apply their ideas if you tell them what they have to do, because they know how to handle the algorithm, the way to solve the problem, even if they don't know anything about what is stemming or what is a fly rock. okay, which can be probably the case in some situations. Okay, this example is an example of another artificial neural network. Nowadays, people don't tend to use the A anymore, in which we have well, I have some. You can see on the left. This is probably what we want to do in our real mind. I love this picture because it's very nice. Probably they have a kind of an artist doing this, and there is some kind of design terminology. No, for those who are not the specialists, me for one, there are several symbols, but you can see, and I'm using my Bardeen meters. These are units. Everything is measured in lengths. So for an engineer, for a physicist, okay, this is not a very complicated unit, is it? So how do you reduce the problem that I had before? No, whole lengths, burden, spacing, stemming, powder factors. What normally is done is that the hidden layers project our input data, which is in the form of magnitudes and units, into some compressed information that is enough to be handed out precisely with the least amount of computing consumption, computing cost. Computing cost is not measured in money, but it's measured in CPU time or GPU time, in processor time. No? And then be able to give some kind of output. For people that are familiar with mining, physics, materials, etc., what kind of engineering, all these units that appears here, this is a unit of density, this is a unit of pressure, because we have the elastic modulus, etc., should be familiar. So in the end, it's a way of simplifying our problem to optimize the way we handle this kind of rock fragmentation issue. Okay, SVR is the algorithm that we're using. Okay, it's technical in this case. This is called support vector regression. When the machine learning field started and neural networks, my elders here in the department used to say that this is a complex regression. So we're not doing anything that is very different from a least squares fit. So we're trying to fit something with more polynomials, with more grades in our polynomial, something like that. I cannot resist to say something that the late John von Neumann said, which was one of the mathematicians and physicists involved in the Manhattan Project, that he has permeated several fields of science. He was Hungarian. Being a Hungarian, as Fermi put it, he was an extraterrestrial. Von Neumann said that if we are able to use 4 parameters for our model, we could model an elephant. And if we are allowed to use 5 parameters, the elephant would move its tail. So, getting lost in the amount of hyper dimensional world in which the mathematicians and the statistical mathematicians and engineers and informatics people live when dealing with this kind of hidden layer problem of neural networks would make von Neumann extremely unhappy, because he would see no physics involved in there. But of course, quantum mechanics, which was something he was involved in developing at the time, was also something mystical, something that didn't have an explanation in their mind. So we are facing some kind of world that we don't fully understand, but it's extremely helpful. So again, going to the human factor, what do we want? To know everything we're doing, or to get some revenue and be able to do this as fast as possible, clean, sustainable, recover this in green, and get everything done as properly as and nicely to give something to our customer that she values most of all. This is the ongoing discussion at the moment. Okay, so if we move on to drone technologies, well, you can see that we can use technologies in surface, these technologies in surface mining, but we can use this also and this is really true also in underground mines. What is the use of a drone? A drone has cameras, has sensing equipment, really simulates the modulus that we sent to the moon and elsewhere in the solar system, etc., to gather information. So they are really important if they are able to submit the information they have, if possible, in real time. Now, this is not easy in some environments. So you're mine 800 meters underground, maybe the connections are not as good as they should. So you probably have to repopulate with several repeaters and access points. And okay, you need to have some kind of pre-processing also to be able to use this. The idea is to have people that are able to reinterpret the images, and in the end, this is what I was mentioning about the underground mines, and in the end, from that, obtain information that is useful to improve the exploitation of that particular project. So with this, we are dealing with visual interpretation. We are doing with techniques that have been used for years in remote sensing in general. So we need to be able to analyze pattern recognitions and to inform the machine and be able to check this. So in fact, what you can do is to, of course, you need to first take out the drone and say, okay, we will do it this way. We will handle it this way. We have some experts that are able to play with this. This would be lovely for children, as you know, because it's kind of fun. I mean, the drone could be very expensive, so if it falls and breaks, it will be not nice. But the idea is that we are able to play as if we were playing in front of a computer or using even joysticks, etc. So we have to interpret this, we have to fly the drone, and then it takes images, and then we deal with techniques that are able to interpret and do pattern recognition. No? This is a case in photogrammetry, in which we will be able to explore this. I think it was a copper mine, and there are several places, and we can take images. As you know, the electromagnetic spectrum is wide, so we are not only talking about visible light, but we will be able to obtain images in the infrared spectrum, and this can also interact with seismic, kind of, let's say, traditional, and even if it is not that much, equipment in which we are able to obtain data that come from induced small S or P waves that we have around. And with that, we conduct our surveys, which are kind of non-destructive, before we really drill our holes and try to check out if everything has been interpreted correctly. This, I think, it is not really new for any of you, I think, because it's something that has been going on for a while already. No? And with that, the idea is that we can really obtain information on old mining installations, in which we may try to check out if there is something still worth of mining and obtaining and producing or not. And we can also go to virgin land and check out if there is something that gives us hints that we may be on the verge of having a nice discovery that will be interesting to probe in depth. And this is really relevant. No, I have around the names of this equipment. Well, I don't really think it is really that important. There are, I think, there are even journals, scientific journals now specialized in this kind of equipment, and this involves lots of artifacts that are really new and fall absolutely within the realm of Industry 4.0. But we can turn on also to what happens if we want to go in our mind and minimize the exposure of our human personnel. So in the so-called unmanned mining, in which we don't have persons around, what can we do? We can do plenty of things. We can. This is an example of a navigation finding system. No, you can see in the center an inertial navigation component, and you have a robot basically. What you have is something going underground, moving around. Given that this is not really something that needs very complicated. The terrain is not extremely complicated to move on. Everybody has images of rovers that landed on the moon and other planets and are able to explore this kind of aggressive environment. So we can have some kind of all these orange, yellow squares tell you about different instruments that the navigation finding system has, in which you can later on integrate this and communicate with the controller, which can be human or not, and give a picture of what is happening in this particular environment. No, this can be extended. We can have a full process control, and we could have a mining equipment that could be fully automated or mechanized at least. No, and you can see there are flow charts, the typical algorithms. So trained minds are able to ask the proper questions, and with this we can say the machine should be trained in questions that are are easily answered with yes or no, to define clearly if we could continue with the process or we have to go back somehow. Okay? The particular example that is shown here is not relevant. It is relevant for the people that designed this and the people that they wrote this paper in energies. But the idea is that we should be able, in our particular case or study case, to divide our problem, simplify it, do some kind of model that splits in smaller pieces our problem, and then try to solve each problem separately and then integrate everything. And this is the ideally is the type of mind that people doing computing programs have. No? So I have this problem, okay, I'm splitting this and access it, and then I need a loop, and I need to go back if necessary, and then I may need to iterate the process, and then I need some control at the end that checks out if everything is correct, gives the information to whoever is interested, and then goes back again and gathers some more information and integrates this in our model again. No? So this is the idea. It's kind of another blockchain architecture. Well, this is real software for mining equipment. So there is something that is taking some pictures in a wall. Well, it's another coal mine. I mean, they tend to experiment with this. Then there is some monitoring system. Well, this is, I think, for a pump. We have some cameras around that are handling the shear. We have some monitors. This is sophisticated software, so to say. There are some statistics, and then we can have a 3D model of the region in which we are doing the mining, no? and cutting out some veins in the material. This is all handled remotely. Of course, you may have somebody sleeping around and taking a nap or some coffee, but there should be some surveillance, and this surveillance should be able to light on a red light, put something that warns you, ideally with some kind of beep or so, because something is going on that is not correct. And if this is done without human intervention, we know that the risk is minimized. We may lose a lot of money, but there is nothing happening to the people that is around. Of course, I told you other examples. So there are equipment, trucks, other drones, etc., that are intrinsically unmanned, but also the control systems should be tried to be unmanned. Now, everybody probably is wondering, where do I have my niche in which I can work on? Of course, this is something that is already even in the press, in the media. What is happening with so much artificial intelligence with traditional jobs? Okay, many of them will be killed. Many of them will be over sooner than later. So this is something that we should be ready to cope with. But there will be others. There will be others. Problem is, for the higher educational institution, because this is an IIT Hey initiative project and webinar, we should be able to be moving forward. And do we, the people that are responsible for producing the materials that are educational, are we as fast? The answer, in my opinion, is no. I mean, I cannot cope with all the changes myself, and I try, and I'm all the time trying to learn, and this goes on forever for all the people that are working in as educators in this kind of academia, etc. But everything goes so fast that it's impossible to handle everything. So teamwork is more important than ever, and recycling and this kind of skills that are called soft but are not that much, in which we are able to recycle ourselves, to have lifelong learning, to go and try to learn things all the time. This is the only way of going, no? And try to learn from the ones that know, because there will always be someone, and you can discuss with these people and say, okay, well, would you be willing to come and explain this to 20 people in a seminar in my company? Oh yes, why not? And this is really the way to go, in my opinion. Collaboration. Okay, you can have cloud mining as well. Cloud mining is, well, I mean, computing in the cloud is maybe something you are more acquainted with. Amazon, Google, Azure, which is from Microsoft, Oracle, sell computing equipment for you. That is done by companies use it very heavily. They sometimes nowadays they don't even have their own servers anymore, their own clusters, their own computing facilities, and they do all the computations in the cloud. Now, cloud mining, you know that we've been using mining in the context of data, the context of cloud. So mining is a very important word, and it also has permeated fields that are not intrinsic to going and try to find some resource to have some new material that we can work with in the industry, because the concepts that permeate mining have been in our heads since the caves, and this is something that people should recognize. You should be proud of working in this field, because it's not. I think that the self-esteem of some people is still quite low in some places, and this is not the case anymore. Believe me. Okay, so we talk about cloud mining. What is this? Of course, this is something that operates our company, for instance, using data that is uploaded to a cloud, to somewhere elsewhere, to a server that is for which we pay to a service provider. We have some vendors. We can play with their computing equipment in close interaction to them, of course, to bring it to be more adequate for our needs. So typically what we do is to upload some data from the production, and store it. And there is a maintenance team that can go back and say this is not okay, etc. There is a cloud platform, the vendors, the enterprise, whatever, that has some standard processing, can even develop some apps that are important for you because we have to be mobile, or some applications with portable computers or tablets or whatever. And then we can even subcontract this, and we can have some personnel that goes and say you, okay, you should take the data this, that, and that way. We can upload and download the resources, and then we have some output that is typical of the end of the line of some kind of business product. And everything is done remotely. Only the production inside is done in the mine itself. And this is really going on at a faster pace every time. And the idea is that we should learn from this. I mean, if you check out some of the literature that I've been using to when I was trying to produce a presentation, etc., it's very, 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 very modern. Some of them are even from this year. And this is something that is an ongoing effort. I mean, people are really tackling the field and trying to bring all this that is state of the art in other branches of technology, and bring it closer to the new mines. Of course, data mining, this is kind of redundant, no? In Industry 4.0, of course, we have mining, we have processing, we have post-processing, we have some, in this case, you can see that there's some energy, we have plenty of interaction with other business, we will have some social acceptance, etc., etc. And you can see here that all this paraphernalia of nomenclature and lexicon that appears every now and then in the economy sections of the newspaper, so Internet of Things, digital twins, as Ramon said before, big data, blockchains, sensors, artificial intelligence, neural networks, machine learning, machine vision, etc. Everything is interconnected. So it really is supposed to really pay off. And the companies that really are driving to do this in advance, that are normally the ones that have some money around to do it, in the end will compete at a very high level. And you can really say that top enterprises are really building up departments that deal with all these initiatives ever and ever more and more. This is because nobody can do anything alone. And this is known from the 20th century already, and some efforts that went in the change from the beginning of the in the interwars years, but that now has expanded completely to all industrial fields because of the internet, basically. Now, I mean, we have not yet implemented mining 4.0, and we are moving on to mining 5.0. I mean, are we going crazy or what? Now, excuse me, I'm going to drink some water. I don't even know if I have to do some pause. Sorry. So what is mining 5.0? What is the idea? What is industry 5.0? I'm laughing because it looks like science fiction sometimes. It used to be science fiction when I was a kid. This is the integration of humans and robots and machines. So you would say a cyborg or what? Not really, but we should be able to have virtual reality, to have as unmanned as possible equipment, to not risk the life of anyone going to a mine, to have everything robotized, to use artificial intelligence to sense what is the needs of the market and to try to advance what will happen with the stock market of some commodity, for instance, to do some digital twinning, we discussed a little bit before in the question, everything like that. So this is going faster than probably some people intended it to be. I'm not good at fortune telling, but the idea is that around 2050, if possible, and we're not having other catastrophes and things like that, which as COVID or others that slow down the process, that in my opinion we will probably have, so we'll have to live with that. This should be some kind of implemented, if not ubiquitously, at least in prominent countries projects. This should be driven, of course, by changes also in the supply chain. No, well, here you have an example. I think I took this from memorial. Well, memorial no, because I think memorial is the word when somebody dies, and this is not the case. From Mineral Economy, which is a journal that deals with all these kind of transverse, multidisciplinary concepts have to do on how do I improve my revenues by spending where I may and not spending where I shouldn't. Linked to the blockchain and Internet of Things technologies, there is a lot of big data going around in many supply chains, and you can see that these are data that have been taken from mid-2019 up to mid-2021, so we have a pandemics going around then in several countries and for several commodities. And this has to be later on integrated into how we analyze this, that is normally called big data, because this data, the number of data here is really extremely big. There are some analytical tools that are available to people that work in basically economy, enterprise, and so on, in which we can monitor incidents and have some tools going around that can be expanded to tackle the problems we had and try to minimize their repercussion, their influence in later projects or this very same, given that we don't have too much money to waste. So there are some kind of numbers. These are numbers from Standard & Poor's. Probably everybody knows these auditing companies. It's on the impact of the COVID-19 pandemic in the mining sector. Of course, there will be numbers. You do look at the other places, there will be other numbers. You have there lots of metals. No, what I still love is that some of them are still mined and dealt with in ounces, other in tons. We could have also international system, etc. So there are lots of numbers. It's not because of the numbers themselves. It's because you have to integrate this in your analysis. And this is something that is not really that simple, no? So people, what they do now is to do some web querying. I think they call it web scraping, using this terminology from scraps. That they are able to gather all this information and then suggest to the CEOs of the company where they should be more resilient, where they would invest more in trying to overcome the problems that they encounter during this extremely hard period. And of course, this is something that is publicly available. There are even regulatory and advisory committees that are taking care of this. And this is not something that is particularly exclusive of some kind of industry or the other, some kind of commodity or the other, some kind of country or one region or the other. This is all around. And these data are there. And there are people that have been specialized in doing this. The paper I mentioned here, I think if I remember correctly, it had around 50 pages. And it's full of data. But these data are open source. They can check this out. What is not that open source is the tools they use to analyze this. They belong to a company and they sell this. They are service provider and they tell you how to do this. So people in big companies should know if they are want to spend their money in that or they don't at a given point. Okay, this is a little bit simpler in this case. So this is the data information value chains in which there is some motion from data acquisition to get some data value. For that, you need very good sensors again. You need a very nice interconnected network. You need some people that are specialized in processing your data and in projecting your data to have new information, to extrapolate, so in simulate, and then to convey this and be able to implement this in the form of an app or a new sensor in new and smart devices. So this, I think, is kind of clear. This is another way of seeing this. This is the data flow value chains in which you have everything that we had before in big highlighted words, moving from the data acquisition to the data value. So this is not privative of the mining sector, of course. This is absolutely general. You can see that the word mine doesn't appear there. And this is something that is at the core of all the new Industry 4.0 and later on, of course, 5.0 approaches that people are taking already. No, so if in our region we have also some tradition of metallurgical steel industry. You go there and you go to an office and they are full of this kind of flow chart diagrams in which they connect all these things to and there are more and more non-conventional electrical or electronic or mining or metallurgical or mechanical engineers. So there are people that know how to handle these kind of things, and maybe they don't come even from engineering, but they come from economics, or they even may come from law, something that you are able to handle large amounts of data and know what to do with them, and to try to program your machine to do it in the most autonomous way as possible. I know I repeat myself a little bit. Now, if you allow me, I want to go to what happens with, if I'm not able to use a drone, can I go somewhere and obtain something from a repository? So the idea of data mining in some place in which nice people have put some information for me to play with. And I want to be able to gather this information, analyze it with my artificial intelligence techniques, and give something new, and then provide something to my client or to my students or to my colleagues or whatever. Okay, you probably know that there is a European satellite that is specialized in gathering data, of course, not transmitting, but uploading data. And this is called Copernicus. That is linked to the raw materials information system somehow. And with that, you can really be able to go and with the data taken from there are many projects ongoing that people have been able to implement and draw conclusions from that. In this particular paper that I mentioned there, which is in a obscure journal called Resources Policy, that sounds more political than any other thing, there are descriptions of several Horizon 2020 EIT projects that have been going on. I think some of them are not yet finished, in which they've taken data from the Sentinel part of Copernicus that are freely available, and they are able to integrate them in their flow sheets and obtain information that is good for these projects in which they deal maybe with the aluminum and other metals industry, or they try to map some region to see if there is some important resources that need to be mined, or at least attempted to be mined, or there are others. I mean, they focus on several of them, no? But you can see that what they do is to try to map, to process data, to do image classification. This is the central flow charts that appear for all these projects. They are all basically taking images from this available wealth of data numbers that the Sentinel-1 and Sentinel-2 have for you to gather, to try with that to improve the results. No, in fact, they claim that this way of approaching the problem, which is non-destructive by nature, will help to facilitate the SLO, the social license to operate, to get agreement from the mining activity. So these projects are projects that are in the cloud, but also in the cloud in the sense that they are not really dealing with field mining. So they are trying to convince the stakeholders that this is worth doing or not. Or you know that when you try to train one of these artificial intelligence neural network models, a bad result is also useful, and most of the times is even more useful than a good result, because it helps you to steer your model and to try to train it in a proper way, and to change the way in which you are exploring your complex hypersurface field of data. No, I come from the materials field, and sometimes we are trying to optimize the position of some system, and you want to go and see if this minimum is lower than this, because all systems in nature tend to be in the state in which they are at a minimum meaning the lowest energy as possible. No, and moving from the intermediate position upwards and downwards demands having some information and trying to go along a slope that leads you to the proper minimum in the minimum amount of time and the minimum amount of resource consumption as possible. And this is in the spirit also of these projects, no, in which the technical advances try to provide tools to support the mining activities using prospection in general, mapping, monitoring, even waste management. They try to find out if there are some environmental benefits. Of course, if something is spaceborne or airborne, the extractive activities are not taking place. Then they try to convince the stakeholders and get this social license to operate. And of course, they can also help with the regulatory frameworks, no, to facilitate the compliance of these companies with the regulations going around. Even they claim that they can try to help in solve conflicts. I think this is questioning ChatGPT and saying, can you tell me what should I do if this proprietary doesn't want to sell? How have they done this in a similar project in somewhere in another place, etc., etc.? And this you can try to do this, and probably you won't get good answers for the moment. But we are still in 2023, and if they allow us, in 2030, everything will be much more different. Okay, so well, this is some kind of advertising. You know that the Home of Copernicus for Raw Materials has an academy, and there are some courses going around. I don't know if there has been some deadline for that, but there are courses going around for this that are also online, and people, this from our twin EIT Raw Materials, try to teach you how to handle these kind of things. And there are courses that are introductory, but there are also some others that are advanced. If you belong to IIT, they are not that expensive. I think the last one was around 200 euros or something like this. Well, maybe if your company can pay that, it pays off. There are seminars, there are open source things. Well, it was simply to convey this to you. This is another satellite, which is Hyperion. This is Western Australia. You know that Australia, they have a very well-settled and traditional mining industry, which is top of the list in worldwide. And these are typical images that you obtain from the satellite. So the remote sensing, as I mentioned before, has ways of dealing with several layers of images and obtain from there with colors that may be really not that difficult to examine by a layman or a laywoman in the field. In this kind of particular problem, the idea is that the color code will help me to distinguish if it is worth exploring further this particular region. No, in the further right, you can see these are invisible. So in red, you have long wavelengths, short frequencies, and you have mica, and white mica. If it is interesting or not to go and mine this in this particular situation in, I don't remember the place, but it's Panorama area. It's written there, yeah, because I thought I would forget. The MNF is called the minimum noise fraction, so it's the best image you can get. This is kind of routine for remote sensing people. With that, you can suggest, okay, let's go and put some drones over there to be a little bit more certain, and then say, okay, maybe the white mica is full of magnesium or has more iron or whatever, no? And I can be able to mine that and try to obtain some profit from that. This is also the Hyperion data, but no, sorry, no Hyperion. Hyperion is over here, and there are images that can be compared with the previous one, with the Sentinel-2 in Copernicus. With this kind of comparison, people can check out. You can see the minerals. I mean, don't ask me too much. Maybe there are some people in the audience that know what this particular mineral is worth of when mined. But this is an enormous deposit in South Africa, which is the Gansberg one, and this is a surface mine, open air, and the comparison tells you that there is some information that can be cross-checked, and this is really done with an approach that is dealt with this Nmap. The map is a software that is dealt with a typical algorithm that some people has developed to check out hyperspectral information from these satellites that deal with raw materials exploration. This is more touching a little bit my heart because this deals with magnetism, in which I had some input. I used some squids when I was younger. So these are superconducting magnetometers, and nowadays they are you can use them with they are quantum in the sense that they do. I mean, I'm going to the details, but they do use some quantum techniques to be able to explore, to obtain the signals. And sometimes you need even that they go to temperatures that are close to some gas in the liquid state. I'm saying helium because it would be too expensive, but maybe nitrogen and so on. And they benefit from the application of these sensors. They are airborne, and you can put them in a kind of a drone or maybe a plane because they are not that small. And you can check out several quantities that deal with the magnetization of the material, which tells you something about if you have in iron, cobalt, nickel, for instance. You can check out interpreting some electromagnetic laws. You can obtain information on the conductivity or inversely on the resistivity, or you can even do some density measurements. No? So you can also check out and do some gradiometries, checking out gravity information, no? Gravity photogrammetries and graviometries. And why is this so fun for me? Because we deal with the two real world most important forces in nature, which are electromagnetism and gravitation. And this is also applicable to exploration of minerals. These are sometimes types of images in which you have some color code in a region in central Sweden. Well, I don't know if you could say Sweden is so long that this is central, but this is really close to Uppsala, Stockholm, not that far away. And you can see there that this is a geological map that okay, it's said here, no, Bledberget. You can obtain information and from airborne squids that tell you that there is some kind of mineral, and then somebody has to interpret this and say, okay, we can go and deal with ground, more, let's say, conventional techniques and do some tests there physically. But this is kind of important in the sense that it allows you to explore large extensions of ground, no, simultaneously. Or in the autonomous mine of the future, well, you can have something like this, in which you integrate, as we discussed before, from the mine design to the communication or the material characterization. So you have several places in which you integrate technologies. I mean, the input ideally should be green, so you have these solar panels here and these windmills, and then you have some machinery that should be as autonomous as possible, and you communicate one with another via satellites, and you characterize the materials there in the underground mine. You can have robots, all these nice ideas that belong to mining 5.0. People are already designing this. So what I see is that as technologists and scientists, people still always try to project them a couple of decades in the future. And this is now a project, but maybe soon is a reality, no? There is already a project, I think the name is somewhere over here, yeah, that is devoted to specifically trying to design the components of the intelligent mining of the future. No, this is a consortium that is based absolutely, I think, in Europe, except for some mining company in Australia, and it's really not at a high TRL, so really tackling the complexity of all that should be tackled with simultaneously, no? To be able to give some input to the stakeholders, to the partners, but not only to EIT and raw materials, to all the universities, and it has some educational component, has 5G means in this case connectivity, so informatics and telecommunication component, but also artificial intelligence, how to monitor, how to put robots in there, have vehicles, etc., etc., etc. Digital twins, as I said, there is something about that. There are people that have already proposed an architecture, still in the design phase, to be able to check out if this could work in the very demanding environment and harsh environment that a conventional that a new mine should have. So there is something dealing with the physical space, no, drilling, autonomous vehicles, exploration. Well, there is something that deals with the communication. So this is a gateway that has to do with Internet of Things. This is for that you need to take some data, you need to be able to have something that reacts to that data, you need to control, you need to communicate, etc. There will be some cloud repositories in which you store all your information, and you can query this You can see there is input, output, there are arrows connecting everything. Then you can go to the real digital twin, which would be some virtual space using virtual reality. And I mean, this is still, as we discussed before, difficult and not feasible at the moment in many of the real environments that we have at hand. And the idea is that this goes to the cognition phase. So there is some artificial intelligence that is driving everything and is giving the okay or not, and is doing all the checking, and is doing all the post-processing, and is doing all the decision taking. And in the end, is able also to communicate with the public, to communicate with the people to put in the money, to communicate with the workers, and to do some briefing, as is the word that is explained here. No, these parts here are ideally the aim of this incorporation of new technologies to the field, but still are simply in the pre-design phase, I would say. Well, about robots, some pictures. These are robots that are prototypes. There are other types. I checked this in a journal that deals with processes. Of course, they look, as you can see, they look like rovers that won't go to Mars and explore things, because it's kind of very hard environment in which probably there is not so easy access to nice conditions for people that are alive. In fact, so there are others I've seen also, but they didn't have the time, sorry. Some other designs to do some underwater mining. There are other designs already for exploring the moon, and maybe later on some other planets. I mean, there you probably know that the problem is how to transport equipment, because some of the equipment that we already have will probably work, but the problem is we need to have in principle, the new projects from NASA. Then the idea is that we have some base in the moon at some point in the next decade. Let's see what happens. But crazy ideas and dreaming, this is something we cannot be stopped from doing. Being more primary, this is a life cycle analysis with that deals with recycling, because we should have some words also in how this affects recycling. Of course, artificial intelligence is sorting out already scrap and waste in our typical circular economy reprocessing and recycling facilities from our trash, or everything that we put out our door on our trash containers in the neighborhood. And this is something that has still to deal with some low recycling rates. This is old because it is from 2011, but the United Nations organism that deals with it hasn't published anything, as far as I know. It's not easy to reprocess some elements, no? Among them the rare earths or lithium, because at the time this was done, lithium was not even critical. Lithium has entered criticality after 2017, and the new list is quite scaling positions. And there are metals that are more easily dealt with than others, as you can check there. These are the recycling rates, and these are the recovery percentages. So the fraction of scrap that you get in the total metal input that you put again in the industrial value chain. There are some metals that still remain in the red. So some of them, if you have it from scrap, good, we will use it. But some of them, even having them back into the value chain is not that easy. Of course, there is also a line algorithm processing for barriers that we still have to the circular economy, not only mining, but for everything that has to do with goods that we pass on to our consumers. And we know that we are all consumers, and I think, in my opinion, they want to stay in our life for us to spend more time here and pay for more things and more gadgets and more stuff that we need, or maybe not. But this is another issue that is kind of philosophical. And because I'm driving to the end, these are projects that try to deal with batteries, for instance. No, so between the raw material extraction and the disposal, we should be able to optimize these projects. You know that there is a big project now. I think it is 1 billion. Well, for the Americas, 1,000 million euros in the EU. In the EU, sorry, UE, no, EU for you, UE for me, because I'm Spanish speaking person. So all this intermediate process, all this should be linked to platforms that deal with artificial intelligence model-based architectures, if possible, because this will, of course, improve a lot our recycling of these very relevant in metals and other graphite, etc., that we have around in our value chains. I mean, if we want to deal with sustainability, recycling, everything should be a must. Artificial intelligence, informatics have also lots to say. For the moment, they tell us that we're not doing as well as we should, and that's why we have ongoing projects that try to improve this. But the ideal would be to have some kind of comprehensive modeling toolbox that will tackle all the process from the cradle to the grave that our raw material has to undergo to satisfy our needs. And this is far from easy. You can see here again the circular flow chart. If we could put everything back into the value chain, this would help us to improve what is our legacy to the future generations. I don't want to put myself into a very transcendent way of thinking, but we all know that we have some kind of responsibility towards what happens next to the planet. And I think we are late already, but we have to fight. And this is something that humans know how to do very well. So this is really, I found it early this week, again, from this mineral economy. In the value, when you try to deal with business risks and opportunities to do some kind of SWOT analysis of the problem, now that you can see that everything that has to do with environment, social, governmental is top of the list. But I think this is due, it changed from 2021 because of the problems that we had with, from 2022, sorry, with the Ukraine-Russia war. And geopolitics is scaling, climate change is ever scaling, and there are other places in which earning money seems not to be so risky, which I mean, to me, it makes me laugh, because in the end, CEOs and people who you have to convince and governments to spend money, always thinking of the expense. Of course, license to operate has gone, now is closer. I mean, it is to the right, means it went down from the previous list, and this is the present position at the moment. And this will change again next year. So, funnily, digital and innovation seems not to be so important, because it has gone down. It was number 2, and now it is number 10. You see, number 9. So this is because people are more worried about their immediate future, and this is something very human. So if you have a COVID pandemic going around, who cares about having a better Internet of Things application in my work, because I cannot go there. So this is the kind of issue I really think that we should be aware of. Sorry, because my battery is going down, but I think with this I'm finishing. This is me. So if you need some information, I'm always available at this very easy email. With that, you can. I want to thank you having stood by me and listening to me all this long time. And if you know more than me, which is probably the case in some of the fields, I will be happy to have some discussion, be it now, be it later on. And stay tuned because there are lots of changes coming. Thanks a lot.
Okay, hello everyone, I'm Fotis Zachopoulos. Sorry, before I start, can you see the full screen or the presenter's view? Because it's a bit weird with two monitors. Is it full screen?
Yes, it's full screen.
Thank you. Okay, hello, I'm Fotis Zachopoulos. I'm a petroleum engineer and a PhD candidate in the Department of Chemistry at the International Hellenic University. This course is a part of the Embedded Intelligent Technologies for the mining and raw material sector. This course was prepared by using the equipment provided by the International Hellenic University and the Master of Science in Oil and Gas Technology. The course is divided in two parts. The part 1, which consists of a theoretical background, and part 2, which consists of the virtual training session. Part 1 includes topics such as the fundamentals in drilling engineering, some information about drill rigs, rig primary systems, the drilling procedures, drilling rig equipment, and an overview of the drilling simulator, the DS5000. Part 2 includes an overview of the drilling simulator and the available physical and virtual equipment, and the procedures of drilling and making a connection, and the procedure of tripping in and out of the well. Let's start with the theoretical background. The oil and gas industry can be divided into three main sectors: the upstream, the midstream, and the downstream. The upstream sector includes all the operations responsible for exploration of oil and natural gas, the development of oil and gas fields, and all the production operations. Moving to the midstream sector, it includes all the operations responsible for the transportation of the raw materials, which are the crude oil and the natural gas, the initial processing and stabilization of the fluids, the storage of the crude oil and natural gas, usually in big tanks or even subsurface, and the distribution, which can be done using tankers, trains, trucks, or pipelines. The downstream sector includes all the operations responsible for refining the raw materials and the production of the final products, such as gasoline, diesel, plastics, etc. There are also other industries that support and connect various operations in the oil and gas sectors. Now, to keep this course interactive, we have added several questions in the form of multiple choice. Don't worry, you will not be graded for your answers. We will be running some polls in Microsoft Teams just to keep you engaged. So let's start with the first one. Lina, please, if you can start running the first poll.
Yes, give me 1 sec. Launch.
Okay, I will read the question. So what do you think? Which sector accommodates the drilling operations? The upstream sector, the downstream, the midstream sector, or the supported industries? Let's run the poll. Will we have the answers on the chat when we end the poll?
Sharing, actually, can you? 1 sec. Yes. Continue.
I see the poll with all the questions together. We need just to answer the first one at this point.
The first one, yes.
if it is difficult to do so, we can just use our chat manually, just to have the answers there. But we can try the poll if you want.
Unfortunately, the poll is in the poll we have all the questions, so there is no opportunity to have only the answer of the first question. So maybe the best one is just to write the answer and then conclude upon the answers in this question.
Okay, no problem, no problem.
So maybe the poll is not needed right now. We can just see the question in the screen and then answer in the chat.
Yes, yes, directly. A lot of people have already answered the question, I think. So the answer here is primarily A. So let's continue. Here. So, okay, a lot of you have already answered the answer A. So the correct answer is the upstream sector. As we said, it includes all the operations responsible for the exploration of oil and natural gas and the development of oil and gas fields. And as we'll soon understand, these operations can be done by drilling oil and gas wells. Next, the upstream sector can be further divided into three sections: the drilling engineering, reservoir engineering, and production engineering section. Let's read some of these definitions just to have an idea for each one. The drilling engineering is a branch of petroleum engineering that deals with the design, planning, and execution of drilling operations for the exploration and production of oil and gas. The goal of drilling engineering is to safely and efficiently drill wells that can provide maximum productivity and profitability while minimizing the environmental impact. In terms of the reservoir engineering, is a branch of petroleum engineering that deals with the study and management of oil and gas reservoirs. The goal of reservoir engineering is to maximize the recovery of hydrocarbons from underground reservoirs while minimizing costs and environmental impact. Finally, production engineering is again a branch of petroleum engineering that deals with the design, optimization, and management of oil and gas production systems. The goal of the production engineering is to ensure that the production of hydrocarbons from a reservoir is optimized and cost-effective, while also maintaining safety and environmental standards. Now, in order to extract the crude oil and natural gas from the subsurface reserves, we usually have to develop a field. The field development consists of several phases, and in each phase, different operations take place. Initially, we start with access and data processing. During this phase, we need to grant access to the location by obtaining exploration and exploitation licensing from the government. We collect all the available data from the area by running seismic surveys and gathering data from other offset wells, if any. The second phase includes the exploration. In this phase, we have to answer the question if there are any hydrocarbons in place. We do so by drilling the initial wells, which are called exploratory wells. Moving to the third phase, we have to answer the question if the field is worth developing. Now more wells must be drilled. We call them appraisal wells, to map and find the reservoir boundaries. The next phase is the development of the field. Includes drilling more wells, the production wells, in order to maximize the production of the hydrocarbons. Next, we go to the production phase, where we should deploy all the required facilities to transport the produced fluids from the wells to an initial storage, let's say. We should also maintain these facilities and the drill wells by running various interventions and services. The last phase of the field development is the abandonment of the field. And at this phase, and when the field is not commercially exploitable anymore, we should stop the production, plug the wells, remove the installed equipment, and restore the whole area to its initial state. In order to develop a field, as we said, we have to drill several wells. Depending on the phase and the required operation of the well, we can categorize these wells in various types. So we say we drill a wildcat well when little or no previous drilling exploration activity in an area without proven hydrocarbons. Exploratory well is a well where the geological target is selected on seismic data and geological modeling. No previous drilling in the prospective horizon. Appraisal. The appraisal well delineates the reservoir boundaries usually drilled after the exploratory discoveries. The development producer is a well when we drill it into a known reservoir. A development injector is a well used to maintain the reservoir pressure. Water, gas, steam are injected to flood the oil and gas toward the designated producer. An infill well is when we drill in non-productive portions of the reservoir that have not been properly drained. This is usually done later in the life of the reservoir. A re-entry well is an existing well re-entered to deepen, sidetrack, complete, or recomplete. Now, let's start understanding the basics behind an oil and gas well. This is the structure of the well when it is completed. The main parts of the well are the casings, the cement, and the completion equipment. We drill several holes and run the respective casings in order to create a telescopic, let's say, structure, as seen in this picture. This structure is a result of the pressure profiles found subsurface, which force us to use casings to avoid fracturing the formation and allow us to drill deeper. In terms of the casings protect the newly drilled hole, consolidate the unstable formations that have been drilled through, separate any different pressure regimes, provide structural support for the blowout preventer, protect sensitive formations from contamination, provide a suitable environment for the installation of production or testing equipment such as packers, tubing, line hangers, etc. We use cement in between the open hole sections and the casings, or the previous casing, in between the previous casings and the currently installed ones. The cement supports and seals the casing in place and protects it from collapse under pressure. Supports the walls of the wellbore to prevent formation collapse, provides zonal isolation between the formations, protects oil-producing zones from salt water flow, protects the well casings from corrosion, and finally, reduces the risk of groundwater contamination by oil, gas, or salt water. We could say we have four basic casings here. We have the conductor casing, is installed to isolate all the unconsolidated formation. We have next the surface casing, which isolates the water tables. We have the intermediate casing, which its primarily focus is to isolate all the troublesome formation and the overpressurized zones. And finally, we have the production casing or a production liner in case. We say we have a liner in case that this pipe, this casing does not extend to the surface, so it's a liner. So we have the production section, the production casing in order to connect, let's say, our structure to the reservoir. Now, when the well has been drilled and casings are in place, in order to produce our well, we have to complete it by installing the production equipment. The production equipment consists primarily of a tubing, which is inside the casing, and it allows the hydrocarbons to flow. A device called packers, which are used to seal off and prevent flow from the annular space between the production casing and the production tubing. And we use perforations, which are explosives, to shoot holes in the production casing in order to initiate the flow, to create this conduit, this path from the oil to flow to the surface. Another question for you. Is it possible, what do you think? Is it possible to create a section without using casings at all? Will not run the poll, just...
Yes, I will do it by default, no worries, submit. And doing by the poll, can you see the yes results? Yes. Can you confirm, Fotis, please?
I can see the poll, but on the chat, only the question, not the multiple choices right now. I'm not sure.
Yes, Lina, no worries about that, because we can see the question, so maybe they can just answer the question into the
okay.
chat.
Okay,
yeah.
it's fine.
It's fine.
Let's keep it simple. Let's use the chat. So again, is it possible to create a section without using casings? What do you think? Yes or no? Are we going to be 50-50 here? Okay, a lot of you have already answered that yes, we can create a section without using a casing. A lot of you, some of you say that no, we cannot do it. Let's see. Let me come back. The correct answer is yes. When we drill the last section of the well, the production section, if we found a solid and consolidated formation, we can choose to leave the section without casing. When we do this, we call this section an open hole. So we can have a well with an open hole completion. So the correct answer here is yes. But usually only for the last section of the well, the production section, which can be an open hole section. Now, let's move on.
Fotios, let me, sorry I interrupt you, but let me also mention something here, that in the first years of drilling engineering, actually they drill without casing. So this is the reality, because the wells that they drilled were very shallow wells. So there is no need for a casing. After then, when the drilling engineering became, let's say, a science and more sophisticated, then they started drilling with casing because of the depth and because of the various kicks. And as a kicks, we mean the abnormal pressures that maybe face bottom hole. So yes, the correct answer is that we can drill without casing, but we have to take into account all of these parameters that Fotios mentioned before. Thank you.
Thank you very much, Mr. Koginos. So let's move on. Let's the devices used to drill a well. We call them drill rigs. These are several types of drill rigs that can operate in different environments. Starting from your right hand side, we have a land rig which is installed on the land. Next, we have a drilling barge which can operate in very shallow waters. A jack-up rig. It operates at water depths up to 500 feet. We have a semi-submersible oil rig which operates at water depths up to 10,000 feet, and the drill ship which operates at water depths up to 12,000 feet. Now, several factors could affect the selection of the rig. Of course, we cannot run a land rig in an offshore environment, so this is the type of rig and its applications. The rig must be available at any time of the drilling operations, so we have to consider the availability. The drill rig must be able to drill through the required water depth. The drill rig must be capable of hoisting, which means to lift up or lower down the required weight of tools, which is our casing string or our drilling string. So the derrick and equipment capacity must be considered as well. And finally, the cost of its type must be considered as well. Now, we can divide the rotary drilling into two main categories: the offshore or marine rigs and the onshore or land rigs. The land rigs can be further subdivided into conventional and mobile rigs. In the pictures, we can see a conventional rig, a jackknife rig, which can extend its derrick to the required height, and the portable mast rig, where the derrick is folded and can be unfolded when the rig is deployed in location. Floating rigs are a type of offshore or marine drill rigs. A semi-submersible rig is designed to float. This is at your left-hand side, the left picture. Computer-controlled thrusters counter the constant pushing of wind, waves, or currents and keep the rig positioned above the well. This rig type is used to moderate deep water up to 3,500 feet. The drill ship is a floating rig, again, like the semi-submersible. However, this rig can be used in water depths up to 10,000 feet. Another type of offshore drilling rigs is the bottom-supported rigs. A jackup rig has a floating hull and retractable legs, which can be jacked down to the seabed. Jackup rigs are used in shallow waters up to 350 feet, and barge rigs work in shallower waters, usually less than 20 feet. After being floated to the drilling location, the hull is brought to a rest on the ocean floor, creating a stable platform for drilling. Another question. What type of rig would you choose to drill a well in a location where the water depth is 200 feet? Would you choose a semi-submersible rig, a drill ship, a jackup rig, or a jackknife? What would be your choice in this case? What do you think? A semi-submersible, which is a floating rig. A drill ship, again a floating rig. A jackup rig, which is a bottom-supported rig, or a jackknife. A semi-submersible. A jackup, okay. Two choices till now. Okay. Okay, let's see which one. Let's see. Okay, let's see the correct answer. A jackup rig, because it would be a good option here, because it can operate up to 350 feet or maximum at 500 feet. Other rigs, as you said, the semi-sub or even a drill ship, could also operate in this case, but their cost would have been exponentially increased. So the best choice would be a jackup rig. On the other hand, a jackknife rig could not be operated in an offshore environment because it's a land rig. Nice. Let's have an overview now of a drilling rig.
Podios, may I disturb you a little bit? Just to give an instance for that, in case that we would like to rent a drill ship and drill for 1 day, for example. In such a case, like the Deepwater Horizon, the daily rate is more than $500,000. This is the daily rate. It means that you have to pay this amount per day. So you can understand that it is not a cost-effective solution. This is the reason why we go into a jackup rig. Of course, you can drill with a drill ship, you can drill with a semi-submersible rig, but from the other point of view, the cost is something that you have to take into consideration all the time. This is just one detail that it is important for drilling engineering. Okay, thank you.
Thank you very much, Professor Kokkinos. Okay, let's move on and let's have an overview of a drilling rig. A drill rig consists of several systems and devices. Let's see some of those. The derrick. This is this tower, as you can see in this picture. The derrick is a tall tower-like structure that supports the drilling equipment and provides a pathway for the drilling string to enter the wellbore. The drill floor is the uppermost level of the rig where the drilling equipment is located and drilling operations take place. The drill string, a series of connected pipes that extend down into the wellbore and carry the drilling fluid and the drill bit. The drawworks can see it under this picture, is a system of drums and cables that provide the mechanical force needed to lift and lower the drill string. It is directly connected through the derrick and this drill line to the hook where the drill string is suspended. The mud pumps, a set of pumps that circulate the drilling fluid, also known as drilling mud, through the drill string and the wellbore. We have the blowout preventer, a safety system that is used to control the flow of oil and gas and prevent the blowout and control the uncontrolled release of oil and gas from the formation of the reservoir to surface. The riser, a large pipe that connects the rig to the wellbore and carries the drilling fluid and cuttings to and from the surface. The riser, we see a riser, usually we find this riser in an offshore environment, and it covers this depth interval of water, the water depth of the sea. The top drive system, a motorized device that provides the rotational force needed to rotate the drill bit. We should mention here that instead of top drive system, all the rigs usually use a device called Kelly. It has the same principle and it provides rotation to the drill string and consequently to the drill bit. The cementing equipment used to inject cement into the wellbore to seal it off and provide structural support. Finally, the power systems, which include the generators and the engines that provide the electricity and mechanical power needed to operate the drilling equipment. On the drill floor, and with a direct view to the rotary table, we have the driller's cabin. The driller's cabin is an enclosed workspace on an offshore drilling rig. The driller and drilling crew operate the drilling equipment and oversee the drilling operations. The cabin is typically located on the rig floor, providing a clear view of the drilling operation and the surrounding area. It is equipped with various controls and displays that allow the driller to monitor and adjust the drilling parameters, such as the speed, the direction, the rotation, the drilling fluid pressure, the weight on bit, and a lot more parameters. The driller's cabin is also equipped with communication systems that enables the driller and other crew to communicate with other members of the drilling crew or with personnel, other personnel on the rig or on the onshore installations. The drill floor is the uppermost level of an offshore drill rig where the drilling equipment is located and drilling operations take place. It's a large open space located above the rig's main deck, and it is designed to support the weight and movement of heavy drilling equipment. The drilling equipment on the drill floor includes the drill string, which is a series of connected pipes that extend down into the wellbore, as well as the drilling derrick, the drawworks, the mud pumps, and other equipment needed for the drilling operations. The drill floor is also equipped with safety systems, such as the fire suppression equipment and emergency shutdown controls to ensure the safety of personnel and the rig in the event of an emergency. The derrick, this tower-like structure, on an offshore drilling rig, and both in an offshore and onshore drill rigs, supports the drilling equipment and provides a pathway for the drill string to enter the wellbore. It is designed to withstand high loads and stresses associated with drilling operations. The manicky board is a platform located near at the top of the derrick, and it provides a workspace for the derrickman, who is responsible for manipulating the drill string as enters or exits the wellbore. Now, let's dive into the primary systems of an oil rig. The power system is the system responsible for generating power for the rig. Drill rigs often have to operate in remote locations and so must be able to generate their own power. So we have large diesel-powered internal combustion engines to generate electrical power for rig operations. The hoisting and circulating systems are the major power consumers on the rig. Here we can see the drawworks, the mud pumps, and rotary tables, which are the power consumers of the rig. The hoisting system. The hoisting system is a large pulley system used to run and pull drilling equipment in and out of the well. It consists of several equipment. The drawworks typically consists of a drum around which the drilling line is pulled. The drum is rotated by a series of gears powered by an electric or diesel engine. The operator can control the speed and direction of the drum. The hook, you can see here in the middle, is responsible for suspending the whole drill string while drilling, or the whole casing string. The hoisting of the drill string is possible due to this configuration of the traveling block, the crown block, and the number of spools of the drill line in between. The circulation system is used to circulate the fluid we call drilling mud into the well. So we use mud pumps to circulate this drilling mud through our whole structure. Here we have a mud tank, a pit full of mud. So a huge mud pump sucks this fluid, this drilling mud, and discharges it through the standpipe up to the swivel, through the drill string down to the pit, and then the drilling mud reaches the bottom of the well and returns back through the annulus and goes through a series of equipment in order to be cleaned and stored again in the same tank. So again, the circulation can continue here. But we say we circulate the drilling mud, but why? For several reasons. We need to cool and lubricate the drill bit and the drill string. We need to remove all this broken rock, all these cuttings from the bottom hole up to the surface. We need to minimize the formation damage, and of course, to counterbalance any extra pressure we found in the formation. So we have to control the formation pressures. Now, the well control system is a set of equipment and procedures used to maintain control over the flow of oil and gas during drilling operations. It is designed to prevent a blowout, which is an uncontrolled release of oil and gas from the formation or the reservoir up to surface. The well control system includes components as the blowout preventer, for short is BOP, choke and kill lines, and mud pumps. The BOP is a safety system that is used to control the flow of oil and gas and prevent blowout. It is typically located at the top of the wellbore and includes components such as the annular preventer, the ram preventer, and the shear rams. At your left-hand side, in the first picture, you can see the actual blowout preventer, this huge equipment, which is divided into the annular, the ram preventers, the shear rams, etc. The second and the third picture is the console that we operate the blowout preventer. The red one is an onshore console, usually, and the right one is an offshore unit, offshore console to handle an offshore blowout preventer. The choke and kill lines are pipes that are used to control the pressure of the wellbore by adjusting the flow of the drilling fluid. The rotary system, designed to provide continuous rotation from surface to the drill string assembly and consequently to the bit. There is a rotating machine, the rotary table, on the rig floor through which drill pipes are run. As the hole gets deeper, more sections of drill pipes are added at the top of the drill string at the surface. When the rotary table is engaged, it rotates the pipe and the bit, which cuts away the rock at the bottom of the hole. The main components of the rotary system include the swivel, the Kelly, the rotary table, the rotary drive, the drill pipe, and the drill collars. There are some other related components here, as the Kelly bushing, the master bushing, or the Kelly hose, etc. Modern drill rigs are usually equipped with a top drive system instead of a Kelly. The top drive system is a motorized device that provides the rotational force needed to turn the whole drill string and the drill bit. It is typically located on the rig floor and is mounted on a track that allows it to move back and forth over the wellbore. The top drive system is connected to the drill string and rotates the drill string from the top, instead of using a rotary table on the rig floor. In this case, the Kelly and the rotary table are there and remain as a backup. It allows for the use of heavier and longer drill strings, which can increase the drilling depth and improve drilling performance. The top drive system is controlled by the drilling crew from the driller's cabin or the control room using a joystick or other control devices. We will see this equipment during the virtual session. I think this is our last question for today for the presentation section. Which of the following is responsible for lowering or lifting the drill string or casing string in and out of the well? The hoisting system, the power system, the circulation system, or the rotary system? Please use chat and give your answer. Which of the following systems are responsible to lift or lower down our drill string? The hoisting, the power, the circulation, or the rotary system? Now I think this one it's okay. This poll, Line?
Yes, this one is okay.
Perfect.
Sorry for the other ones. Okay.
Very good. We are 100% A, the hoisting system right now. Let's see. Okay. I think we have a winner here. So, yes, as we've seen, the hoisting system is a large pulley system used to run and pull the drilling equipment in and out of the well. The drilling or casing string is suspended on the hook, which is connected to the traveling block. So yes, the correct answer is A, the hoisting system. We will now be discussing the three primary procedures that take place during the drilling operations: the drilling and make a connection procedure, the tripping out procedure, and the tripping in procedure. The drilling and make a connection procedure is the procedure where a new pipe joint is added to the drill string in order to drill deeper. The tripping out procedure is the procedure where we remove and disassemble the drill string so that the drill bit gets to surface. The tripping in procedure is the procedure where we reassemble and lower down the drill string into the wellbore to continue drilling for the next section. While drilling, when the upper part, let's see the procedure, the drilling procedure. While drilling, when the upper part of the drilling string reaches the rotary table, we should add a new joint, so to extend the length of the drill string and to be able to continue drilling further. The new joint is placed in the mouse hole in case we use the Kelly approach, or a stand of pipes, which means a stand which is equal to three joints of pipes. In case of the top drive approach, is stuck in the monkey board in this case. We should suspend the drill string in the rotary table and release the Kelly or top drive. This can be done by using a device called slips. We now connect the Kelly or top drive to the top of the new joint, and the new joint must now be connected back to the whole drill string. This is the figure number C. In order to establish the connection, either manual labor is used, or we can use a device called the iron roughneck, which can hydraulically connect and secure our pipes. Now we should remove the slips and we can continue drilling further because the length of our drill string has been extended. Let's see the procedure step by step. Here is the rotary table. Let me go here. The rotary table, the master bushing, the Kelly bushing, the Kelly itself, and the swivel. So we are drilling. When and we proceed until the Kelly is down to the rotary table. At this point, we should pull until the joint has reached the Kelly bushing, and now we pull until the joint appears over the table. The next step is to swing the Kelly over the mouse hole and connect it to the next pipe. So stab the Kelly to the new joint. Next step is to bring and align this joint above the drill string, which is suspended on the slips on the rotary table. Stab the new joint to the top of the drill string. Move down until the Kelly bushing engages the master bushing again, and now we can continue drilling. This is the procedure we follow to make a new connection. Now, in terms of the tripping in and out of the well procedure. The tripping out procedure is applied when we have drilled the desired section or depth, and now we need to remove the drill string to the surface in order to run, for example, the casing string. There are often cases as well where we have damaged the drill bit and we have to trip out of the well in order to replace it. The tripping in procedure is exactly the opposite. The drill string is at the surface and we have to restart the drilling, so we have to travel to the last drill depth before we can apply rotation and start drilling again. We'll be having a detailed view of these procedures in the virtual training session. I have also included a very nice video here with the actual procedures, the tripping in, out of the well and making a connection. It's a YouTube video, but I will leave it for how the crew operates and performs these procedures in real time. Let's see some of the basic equipment used on a drill rig. You have the elevators or the elevator. The elevators are used to lift and lower the drill pipe and other components of the drill string during the drilling operations. The elevators are designed to grip the outside diameter of the drill pipe. Elevators come in various sizes and types to accommodate different sizes of drill pipes and drilling operations. We can see here the three basic, at your left-hand side, the three basic types of elevator, and at your right-hand side, we can see some pictures of the crew operating the elevator. Slips. We have drill pipe and casing slips, which are designed to grip the drill string or the casing string and hold it in place while Kelly or top drive are disconnected. At your left-hand side and on the top, you can see the drill pipe slips, while at the bottom are the casing slips. Now, at your right-hand side, you can see some pictures while the drilling crew putting or removing the slips into the rotary table. From these pictures, definitely we can understand that this device is quite heavy. The tongs. Tongs are used to grip and turn the threaded pipes or connections, such as drill pipe or casing, during the drilling process. Tongs are critical for making up and breaking out threaded connections, which involve joining or separating threaded sections of pipe or casing. Modern drill rigs use a device called the iron roughneck instead of using the tongs in order to connect and secure the pipes. This is the iron roughneck. An iron roughneck is a piece of equipment used in drilling operations to make up and break out threaded connections between sections of drill pipes or casing. It is essentially a hydraulic powered wrench that automatically grips and turns the pipe or casing connections, eliminating the need for manual tongs and labor, of course, and reducing the risk of injury to personnel. Now, in the last section of our presentation with our theoretical background section, In this picture, we can see the room where the drilling simulator is placed in the International Hellenic University. Most of these parts of the drilling simulator will be explained in the virtual section later on. But generally speaking, the available devices here are the driller's cabin, the cementing console, the onshore and offshore blowout preventers, the remote choke, and the choke and key line manifolds. The specific version of the system of the drilling simulator provides an API and application programming interfaces for research purposes. This is a view of the driller's cabin, the cyber chair with the screens. We can see the derrick, the top view. We can see a virtual screen here that we can see the subsurface, the drill string, what happens down there. This is an extra screen. In reality, we cannot have such a view in our drill rig, but here we can, but not during the training sessions. And the other touch screens and monitors and joysticks on the cyber chair. These are the offshore. From right to left is the offshore blowout preventer console. We handle the blowout preventer. We operate the blowout preventer with this console. The onshore is the red one. We have the remote choke here and the choke manifold at your left-hand side. I think that's all for the part one. We can proceed with part two, which is a pre-recorded video. So in this section, if you have any questions or want to ask something, it would be better to do it at the end of the video. But still, we can run our polls during the part two, this virtual training. Start. Welcome to part two of this course in the Embedded Intelligent Technologies for the mining and raw material sector. This is a virtual training session where we will be using a sophisticated drilling simulator, the DS5000, to simulate two primary procedures in drilling operations, the drilling procedure and the tripping in and out procedure as well. This training would not be possible without the equipment provided by the International Hellenic University and the Master of Science in Oil and Gas Technology. Let's have a quick overview of the program and the equipment which is available to the students. The DS5000 drilling simulator provides a single chair for cyber-based drilling and well control operations, featuring a large quad-screen graphic display with a central console. It contains weight on bit and other key gauges. A full-size physical remote choke is included, which enables the DS5000 to be accredited for IWCF and IATC accreditation. Additional full-size consoles have surface and subsea blowout preventers, the choke and standby manifolds. The simulator integrates a land, jackup, or semi-submersible oil rig in a three-dimensional environment. Managed pressure drilling mode is also included as a function in the drilling simulator. Starting the drilling operation, the first step is to enable the drawworks and select a low gear as shown in the instructions. At this point, it would be nice to have an overview of our systems and check the equipment status. As we can see, the drill string is already on board, and now we can start continue drilling. At the top of the derrick, we can see the drill string is suspended by the elevators, which are connected to the top drive system. The next step is to calibrate the weight indicator. To do so, we have to pull our drill string up, so the weight on pit will go to 0. And now we can configure the weight indicator, so to start with the value of 0. In this panel, you can also view the rotation and torque gauges at your right-hand side and the drill pipe and casing pressure gauges at your left-hand side. The next step is to connect the top drive system. We have already set the slips, and now we must slack off the weight of the drill string onto the slips in order to be able to disconnect the elevators. Now, let's provide some power to the top drive system so to turn it on. The drill string is not suspended by the elevator, so we can safely connect the upper tooth joint to the top drive system. Now let's spin the top drive to 25 RPM so to establish the connection. Now should also apply some torque, around 5,000 pounds, in order to secure the connection. This small green part of the upper joint indicates that it is safely connected, and now we can start drilling. We should also consider the IBOP, a small device that is installed in our drill string that acts as a check valve, allowing the drilling fluid to be circulated down the drill string but prevents the backflow. We are ready to line up for drilling, and the first step is to start the mud pumps. We are starting pump 1 and pump 2 in our case, and gradually we will increase the strokes of each pump. We can also set a set point for the initial strokes in order for the mud pumps to stabilize. Both pumps have been stabilized at 15 strokes per minute, and as we can see, the discharge pressure of the pumps has been decreased. In the subsurface view, we can see that the circulation has been started and the mud flows down to the bed and starts to return to surface. At this point, we can stage up the pumps to the required flow rate, which in our case is 25 strokes per minute for both pumps. As soon as the strokes go up, the circulation increases and we can see the mud flowing to surface in a faster rate. We are now ready to start drilling ahead, so once more let's pull the drill string up and zero the weight on bed so to calibrate the auto drill. Drill string to be free and start rotating. Checking gauges, both the RPM and torque go up. The drill string now is rotating. You can watch it both on the drill floor and in the subsurface in the virtual screen. As the final step, let's enable the auto driller. First, select the required weight on bed and start the auto mode. From this time on, we should monitor all the parameters while drilling ahead. At a point, the upper joint will reach the rotary table. Now we should make a new connection. Stop drilling, pull out a few feet, set the slips, and disconnect the top drive. In case you need to adjust the position of drill string and lower it down a few feet, just use the elevator again. As an extra step, we adjusted the position of the drill string, and now we should set the slips in order to be able to grab the next joint. The derrickman is ready to provide the next pipe. Release the elevator and move the top drive to the top of the derrick. Several drill pipes are available in the monkey board. Let's grab one and connect it to the drill string. To do so, we should tilt the elevator so the derrickman be able to provide a new joint. Let's pull up a few feet to avoid any potential collision with the drill string. We are ready to connect the joint with the rest of the drill string. Align the joint above the drill string and get ready for the connection. Hopefully, we have available an iron roughneck on the drill floor in order to connect and secure the new joint. Finally, when the top drive is connected back to the drill string, we can continue drilling and we can repeat the same procedure as many times as it is required. Question 1. What is the usage of the slips? A. To suspend the drill string. B. To provide rotation. C. To provide torque. Or D. To provide weight on beat. Okay, so now we can use the poll. Lina has already released the poll on the chat to answer this question. Okay, the question is, what is the usage of the slips? To suspend the drill string, to provide rotation, to provide torque, or to provide weight on beat. Okay, I think all of you answered the same, give the same answer. So let's continue the video. The correct answer is A, to suspend the drill string. The slips is a device used to grip the drill string in a relatively not damaging manner and suspend it in the rotary table. It is often used to suspend the weight of the drill string or the casing string while making or breaking a connection. Question number 2. What is the iron roughneck? A. The crew member who works on the monkey board. B. A device that suspends the weight of the drill string. C. The crew member who works on the drill floor. D. A device that aims to connect and secure a new joint. Okay, again, we have the poll ready. We can use it to answer this question. What is the iron roughneck? A is the crew member who works on the monkey board. B, a device that suspends the weight of the drill string. C, the crew member who works on the drill floor. Or D, a device that aims to connect and secure a new joint. What do you think? Very good. Okay. Several answers here. Several people answered the question. All the answers are the same. So let's forward. The correct answer is D, a device that aims to connect and secure a new joint. The iron roughneck is a piece of hydraulic machinery used to handle, connect and disconnect segments of pipe in a modern drilling rig. The segments can be manipulated as they are hoisted into and out of a borehole. Question number 3. What is the usage of the elevator? A. To suspend the drill string while drilling. B. To suspend the drill string while a new connection is made. C. To suspend the new joint while a new connection is made. D. To provide rotation to the drill string. Okay, ready for our next poll. What is the usage of an elevator? To suspend the drill string while drilling, and not the whole operation, but while the drilling procedure. We are not tripping the well, we are drilling. B. To suspend the drilling string while a new connection is made. To suspend the new joint while a new connection is made. Or D. To provide rotation to the drill string. What do you think?
Obviously, in the previous question, it will be nice to understand for everybody that the iron roughneck is a very strong robot. Actually, this is the device that we call. It's a very strong robot, and instead of have the real roughnecks who are just men, human beings, now we have this equipment, and because it's a very dangerous also job, this is something that it is very, let's say, convenience for them. But actually, it is a robot.
Okay. Now we have a lot of answers to this question. Let's move forward and see the answer. The correct answer is C, to suspend the new joint while a new connection is made. An elevator is used to rise and lower the drill pipe in and out of the drill hole by latching around the top of the drill pipe joints. As the first step of the tripping in procedure, let's set the slips and break out the top drive. The next step is to move the top drive to the monkey board at the top of the derrick in order to grab the next stand of pipes. At this point, we've reached the top, so we should tilt the elevator in order for the derrickman to be able to provide the next stand. Now move the new stand of pipes a few feet above the drill string in order to avoid any potential collision. Align it at the top and start a new connection using the iron roughneck. As a reminder, the iron roughneck is used to connect and secure the connection between the drill string and the new pipe. Ready to continue, remove the slips and continue tripping in the well. At this point, the top of the upper joint reaches the rotary tape. It's a good time to set the slips, remove the elevator, and repeat the procedure. During the tripping out procedure, we need to remove all the drill string from the wellbore. Use the elevator to grab the drill string and pull all the way up till the top drive system reaches the monkey board. When the bottom connection is apparent, use the iron roughneck to break the connection. At this point, because the whole drill string is full of mud, we can use a device called mud bucket in order to avoid spilling the drill mud onto the drill floor. The derrickman is ready to receive this stack of joints and stack it with the rest in the monkey board. this point, we are ready to move the top drive system down to the rotary table, connect back to the drill string, and continue tripping out of the well. We can repeat the same procedure as many times as it is required in order to remove the whole drill string out of the well. Question number 1. What is the usage of the mud bucket? A. To capture the drilling mud while breaking a connection. B. To redistribute the drilling mud into the waste management infrastructure. C. To avoid any leaks or spills of mud. D. All the above. Okay, we can use again the poll on the chat to answer this question. What is the usage of the mud basket we have just seen? A. The usage is to capture the drilling mud while breaking a connection. B. To distribute the drilling mud into the waste management infrastructure. C. To avoid any leaks or spills of mud. Or D. All the above. Let's try this one. Come on, someone must be the first to start. Okay.
How I can write the question?
You can find the poll in the chat if you open the chat, and you can just choose the option, the answer you want, and put and press submit vote when you have already chosen the answer.
Because I'm from the phone, I don't found the poll.
I'm not sure if I can help you here. Maybe Lina knows. I don't know how it appears on the mobile phone, but try your chat, I think.
Yes, you can find the poll on your chat. It's the only way.
Mr. Kyriakidis, are you okay? Did you find how to do it?
Oh, no, I'm not okay.
Okay, otherwise, please type the answer in the chat or just share with us the answer.
Okay, let's proceed and see the answer.
Yeah, sorry, probably it's because you don't have the app on your phone, so if you are in a computer, it will be different.
Okay. Okay, let's move on. The correct answer is D, all the above. Mud basket is a critical frontline tool in managing drilling fluids at the drill pipe. It captures the drilling fluid and redistributes it into the well site's oil field waste management infrastructure. Question number 2. Is the drill string rotated while tripping in or out of the well? This is our last question. Is the drill string rotated while tripping in or out of the well? We've seen two different procedures, the drilling procedure and the tripping in or out procedure. So, okay, it's three procedures. So, is the drill string rotated while tripping in or out of the well? Yes or no? What do you think? Okay, let's see this final answer. A, yes. B, no. The correct answer is B, no. During the tripping procedure, the drill string is not rotated. It is suspended by the elevators, and the top drive system is disconnected. So at this point, the virtual training has completed. So it's a good time. We have asked a lot of questions during this course. If you have any, we are ready to discuss it. So please, if you have any questions, you can discuss them right now. On the other hand, Professor Kokkinos, if you want something to add something more on this presentation and this video, please.
The very good point is that the majority of the students answer the correct answer correctly the questions, and this is very nice because it's not so, let's say, it is not a piece of cake, all of these things. Actually, it is really hard for somebody that has no correlation with these things, with no relation with these things. So I believe that mission accomplished. So best, the students did their best, and we can see from the answer of the questions. Now, I'm pretty sure that there are a lot of questions, and maybe there are questions in the procedure. So I will prefer to ask the audience if there is any question or something that it is not so clear, to just let us know and give some more details on the procedure. It is, from my point of view, I believe that theory is good, but actually when you get the equipment and you try to use the equipment, you try to use the drilling rig, is not so easy. So you have to remember all of these things step by step and do it correctly. And this is what we try to do through the virtual training program. We give the opportunity to those that they have a good experience, and also in some other case a good theoretical background, to apply all these things and see how they can proceed in reality. Of course, virtual reality is not reality, but let me tell you that with this system, this is the only system that you can accredit yourself as a driller. So it is like a pilot, like a flight simulator. Actually, when they train in a flight simulator, it is almost exactly the same with the reality. And also when these pilots retired, the hours that they have spent in the flight simulator, they are counting for their retirement. So this means that the virtual reality right now is very, very close to the reality. And of course, let's take into consideration that all of these things happen in a very safe environment. And in reality, all of this environment and all of this equipment, it is not safe. I mean, it is really hard, and you must be very, very careful. So if you do something wrong, in reality, it will have an impact. But here, the only thing that you will see what will happen in reality, but you will be safe. This is what I try to say. Actually, the petroleum, the oil and gas industry is one of the most safe environment and safe industries. But when something happens, it is like the flights. If something happens, you will be the first page in the newsletter, because it is not so often to happen. So this is exactly what we try to do with this equipment, to prepare people in this critical infrastructure to know how to react in any case. And this is what we try to share during this very, let's say, just 2 hours of presentation. But actually, behind all of this demonstration, there are many, many hours of preparation for all of these things. So if I can see, there is a question. I have a question regarding pumps by Fernando. So Fernando, if you can share your question with us.
Yes, morning, sir. So this is a new topic for me. I'm a methodologist, but anyhow, we are always learning in life. Okay, that's it looks very interesting. I have one question. Well, in my opinion, during the drilling, you yields or produces a lot of slimes, mods. Okay, what type of pumps do you use? Do you use horizontal or vertical? And what type of what's the material of the impeller and frame of the pumps? Do you know? Do you have any idea?
Yes. Fotios, do you like to answer this question, or may I proceed with that?
No problem. As you want, Mr. Kokinos.
Okay. So actually, we have pistons pumps. So we have pumps with pistons and with liners, and we have single stroke pumps, and also we have double stroke pumps. It depends on what we would like to do. Actually, in the double stroke pumps, we use 2 strokes. We have 1 stroke right that fill the liner full of mud, and the second stroke that unfill this mud to the reserve pit. So this is the 2 main categories of pumps that we use: 1 stroke and 2 stroke. We call them triple and double pumps. This is what is the name of the pumps. I don't know if you need any more information on the pumps.
No, it's okay. It's okay, because I suppose that the impeller material should be high chrome steel, because the slurry or the motors is very aggressive. You know, can be can have a lot of abrasion. Okay, but it's okay.
It's okay. Mm-hmm. Yes, and the most important part is that when you take the mud outside from the hole, there are plenty of equipment that start with centrifuging. We start with hydroplaning. So all of this equipment try to return the mud in the initial condition before drilling. So this is why we use the muds, and after that, why we have to retain the whole mud in the same properties as it was in the beginning, because the properties like the pH, also the density of the mud, and all of this information are very important to retain the balance in the pressure at the bottom hole.
Okay, understood now. Thank you.
You're welcome. You're welcome, sir.